Welcome again, if I've already welcomed you. If you just joined, welcome to Aqua Membranes' first webinar. Hopefully we'll be doing a number of these in the future as we get more applications and more case studies. My name's Craig Beckman. I've been here for about 5 years now. I'm the current CEO. Aqua Membranes is a startup that's based here in Albuquerque, New Mexico, and we are reinventing reverse osmosis. So let's go back to the maybe why or the problem, and then I'll jump through today the logistics of how we're solving it, what we're doing differently, why we think we're uniquely positioned. But before we get there, even a little logistics. I'm going to talk here for about 10 or 15 minutes, give you some intro. I'll talk about the machine behind me, what that is. And then we're going to turn it over to our CTO, CJ Kurth, and he's going to go through some more technical slides. We know based on the attendee list, a number of you are already experts in membrane technology and process solutions. And we're sure you'll have questions about concentration polarization, pressure drop, cleaning frequencies, pressure drop per flow rate. And CJ, good news, I'll help you walk through those. And then if we don't address your question, if I don't get to it or CJ doesn't get to it, we have a Q&A section at the end. You can wait, load your question right at the end, or if you want to type it in beforehand, we'll make sure we get to those. But let's talk a little bit about water. Water is something that all of us use every day. Even if we're not directly using it, which would be unusual, the products we use, the car we drive, the food we consume, the beverages we consume, the products we use, the phone in your hand, the computer you're probably watching us on, all of those use water. And for a long time, many people didn't really have an understanding or maybe an appreciation for where the water came from or where the water went. They opened the tap and went down the drain. They didn't think about that. Or they just went to Amazon and bought their new computer or webcam or whatever that thing was. But I can guarantee you all of the people making those products did have to think about that water. And what is a trend that's happening around the world right now is this idea of whatever water you were using, there's a good chance you might not get that same amount. Or if you're building a new factory and you're expanding, let's take the onshoring of semiconductors into the United States again. Those manufacturing sites called fabs require enormous amounts of water. And when they bring them here, they're building them in Texas, they're building them in Arizona, in New York. There's not enough water to build those facilities. So all of this is driving this idea of the water you have, you might not be able to get. The water you do have might be taken or you can't get more. And even in a municipal market, the water you get at your house for, use in food and beverage, but also in cleaning and washing or even watering your lawn, all of that's going to get more expensive. And one of the solutions to that problem is recycling. So whether it's your home, taking maybe some of the water that was lightly used, washing your dishes, and it could be used for irrigation. Some people do this already. Or an industrial facility, and we look at the backside of that facility, and rinse waters or condensate waters that are coming out of the back of the plant can get recycled back to the front of the plant. This is not a new idea. It's kind of straightforward. You'd assume that. And for a while, one of the main technologies there was evaporation. So going back, for lots of human civilization, to purify water, you could boil it and then recondense it. That's still a common application for recycling. Over the last 10, 20 years, membrane technology, what we do, reverse osmosis, was used in addition or even replacement to that evaporation. But that application for membrane technology to solve a huge global problem has always had an Achilles heel: energy and life of the elements, or the fouling that limits the life of those elements. Those are huge problems to be able to do that recycling better, or for some customers to do that recycling at all. Like their only choice was evaporation, which is very energy intensive. They couldn't look at membranes. But Aqua Membranes is helping solve that problem for those customers that couldn't use membranes, but also people that are already using membranes, and trying to help on that kind of big detriment to membrane use in this recycling kind of idea by lowering the energy to do the same process. So same volume, same quality at lower energy use, or actually maybe even enabling it because of the scaling, fouling, mineral buildup that application had maybe it wasn't even possible. And that's the problem that we're fixing. So you might ask, well, how? Like, how is Aqua Membranes, this little startup in Albuquerque, New Mexico, solving a big global problem like that? Well, one of the key items is the printer behind me. This is actually a large format printer that we've modified to print in 3D. Now, we sometimes jokingly around here don't talk about it as 3D printing because a lot of people think that as like a structural part, like a plastic part of my refrigerator broke, I'm going to go 3D print a new one. That's not what we're doing. What we're doing is actually more like 2.5D printing. And what I mean by that is we print wide in the X and Y axis, but very short in the Z axis. And what we're printing are features on top of a membrane surface that then enables a flow channel that is more custom designed. So kind of reverse osmosis 101. I won't go too deep into this, but a couple of things you need to know if you don't already. Reverse osmosis is a separating device. So one stream in, two streams out. One good stream, one bad stream. Also, that separating device is kind of like an envelope wrapped around itself. And as you wrap it around itself, it's kind of logical you need another layer in there. Otherwise, there'd be no way to get water in contact with that membrane. For really the entire life of this technology, which goes back about 60 years now, a extruded mesh material was used as that layer. That is what we are replacing. That is what we are fixing with this printer behind me. So we take raw membrane from the market, roll it through the printer, and then as it's rolling through, we actually have a print head going back and forth, putting down a proprietary polymer that then creates features. Well, what are those? They're dots, squares, lines, triangles, chevrons, kind of whatever we want. The important part is that we're able to customize that to optimize the right flow, pressure drop, and mixing in the membrane element, which then makes the membrane element work better in that recycling application we talked about, which then actually enables literally the construction of the plant. Like if you're trying to build a new fab in Chandler, Arizona, for example, I'm willing to bet the city of Chandler is going to say, no, you cannot have 5, 10, 15 million gallons of new water. You're going to have to find it on your own. Go recycle it from somewhere else. But that's going to be a challenge with existing technology because of that mesh layer. That mesh layer is what caused a lot of the energy loss and led to premature life failure or shortened life of those membrane elements. Materials that get clogged up in that spacer material and that flow channel, you could clean it out, but then you'd have to bring the system down. Eventually, you can't clean it anymore, and it has to be replaced. That's the problem that Aqua Membranes is excited about solving. So how we solved it, one is this printer, which has been years, literally years in development. This is version number 5 or 6, depending on how we count them. And then the resin that we put on the membrane surface is really important. It has to be neutral, meaning it can't cause harm to the water. It can't leach things in the water. It has to be pH stable, and it has to stick to the membrane. So those are a lot of the development we've also gone through besides just getting it down to the membrane, making sure the polymer we use is appropriate. And then what is the pattern? I said before we could print circles, lines, triangles, chevrons, whatever. What is the pattern that most effectively optimizes that flow, that production of the system? That started in a computer model, and then we print different patterns here. We test it at our facility and then test it at customer sites as well. So then maybe you go from, okay, I understand the problem. I understand the solution. I understand now how Aqua Membranes is doing it, at least at a high level. CJ will take you into more details, but like why Aqua Membranes? Like why are they uniquely suited to do this? Well, one, we've been doing it for a while now. Rodney Harrington, our founder, has been at this for more than 10 years, which sometimes in the startup world is seen as a drawback or a detriment. I actually love the fact that Rodney's been at this 10 years because it's proof of how difficult it actually is and why maybe somebody hasn't done it in the past. Rodney is tenacious. He was willing to say, look, I know it's difficult. I know a lot of people in the industry that are experts have said, you can't do that. The membrane's too fragile. You'll damage the membrane. You'll cover too much area. But Rodney, in his determination and stubbornness, perhaps, said, no, we can figure it out. We're going to figure it out and do it. And we are. This is now a commercial product. So you can hear the printer running behind me, perhaps. That is actually printing membrane elements that will then go into the field for customers in the mining industry, the food and beverage industry, the microelectronics industry, the industrial water reuse industry. Those are all customers that are buying products from us today. The other reason, kind of why us, we own all the IP. Through this journey, Rodney's done a great job filing patents that cover the patterns and the pattern attributes and a number of the manufacturing techniques that we use. So that's kind of the problem, how we're solving it, why us, and then maybe like who is our target customer? Like where's the beachhead we really think we can add value to? One segment is microelectronics. Micron Technologies is actually an investor and a customer of Aqua Membranes. They were coming under a lot of pressure from their biggest customers, Microsoft and others, for data centers. So you probably know about data centers and their explosion with AI and other just everybody storing everything digitally. Well, those data centers consume enormous amounts of memory chips. Those memory chips are made by primarily Micron Technologies. So to be a good corporate citizen, Micron knew they had to do better. They had to use less electricity, less water, less chemicals, et cetera. And when they looked at the water space, Aqua Membranes was their choice. They looked at hundreds of water technology companies and thought, this is the one that will get us the furthest along. And we're saving them enormous amounts of energy already in their fabs around the world. You can check out more about case studies that we have on our website. Other customers, food and beverage. Again, a very consumer-based facing company where kind of their license to operate is going to be measured a little bit on how well they do with the resources they use. In the beverage industry, it's very common for them to be measured on how much water goes into the plant versus how much product do they produce. And getting that ratio better and better is affected by water recycling, right where we started. This idea of recycling water back into the beverage facility will help them improve the ratio of product to water used and increase their connection with their customer base and even their investor base. We're just starting to see this now. Investors, pension funds, universities, endowments are looking at the investments they make based on sustainability and being good environmental stewards. All of this is stuff that plays into tailwinds for us at Aqua Membranes. We couldn't be more excited about our future. We're ramping up. We're excited to talk to you about pilots, and hopefully you'll pick up some more from this webinar. In just a minute, I'm going to hand it over to CJ. He'll get a bit more down into the meat. But remember, if you have some questions for me about customers or anything else, or CJ's, go ahead and post it, and I'll circle back after CJ's and help answer those questions. Take it away, CJ.
All righty. So I am going to start showing some slides here. Let's get this going. All right. So one of the things to think about with the stuff that we're doing is why the feed space or why the feed channel. There's a lot of parts of the membrane, membrane element. Most time people think about the chemistry in the top layer. Feed channel has actually been described before as the secret of membranes, that it's sort of the piece that people forget that has a huge amount to do with performance of the element. And one of the things that we can do to recognize that is to think about where space goes inside an element. Because most of this industry has been kind of built up around the concept of these cylindrical spiral-wound membrane elements, 8-inch diameter, 40-inch long. See a cross-section on the left here. Because of the symmetry, it's actually pretty easy to calculate how much volume is going into the different components. The central tube you can see in the middle of there, the feed spacer, the membrane, even the permeate carrier, some of those things. And what quickly becomes apparent is that extruded mesh netting that's used to create the feed channel takes up most of the volume of the element. So as we think about ways to make the space more efficient, it's the biggest bang for the buck in terms of improving performance. So how do we do this? Well, you can see in the bottom right here, that's a picture of the extruded mesh netting. What we end up doing differently is going to these print patterns. So at the bottom, you can see that little insert of some features on the surface. This is what was being printed on the printer behind Craig a few minutes ago. Slightly different pattern than this one. Each of those patterns can be optimized for different applications. But because we have the ability to shift dimensions around quite a bit, the current product that we're making goes from a 28 mil mesh, like we saw in the previous slide, to a little bit under 20 mil for the print. And by taking advantage of that extra 9 mils, we can get more membrane, we can get more permeate carrier into the element, essentially more leaves in the same outer value, and the same outer dimensions. So that's kind of why we're focused on it. It's the biggest bang for the buck in terms of space. What's important to think about is, that is also something that's available with a mesh or any other material. You can go thinner, you can end up getting more membrane area in there. The pressure drop is the reason that it typically hasn't been done before. So in here, what I'm showing is an active area for an 8-inch element on the x-axis, and then pressure drop at 40 GPM on the y-axis. And you see two different curves. The blue is a mesh. So the 400 square foot typically has a 34 mil mesh feed spacer. You take it to 28 mil mesh, you get about 440 square feet. And at that same flow rate, you can start to see the pressure drop increasing. And it makes sense. There's smaller channels, there's more obstructions, higher pressure drop for the same flow. The big difference is that by optimizing the print pattern, we can go to a much lower pressure drop curve as a function of channel height, or essentially active area. And sometimes in membrane space, people talk about a goodness curve, or if it was back in the gas separation space, a Robeson plot. I was looking at kind of membrane water transport versus salt transport. And this is to some degree almost like a goodness curve for the feed spacer, how efficiently it's able to get water through the channel. And the fact that with the printing, we're able to do that at a much lower response curve there. So for a given active area, we could have a much lower pressure drop, or for a given pressure drop, we can have much more active area. But specific points that we're talking about here, that second red one, that's about 505 square feet, that would correspond with the previous plot that I did at the 19.5 mils. Well, when we start talking about pressure drop in the absence of anything else, one of the things that is likely going through your mind is the effect on concentration polarization, because if we wanted to get the lowest possible pressure drop, we would design a channel that goes to a completely laminar flow. But then the idea is that mixing would suffer. So we've done a lot of work internally on concentration polarization, first with a lot of CFD modeling, later with a lot of experimental work, and a fair bit of back and forth to get to the print patterns that we're currently using. In the interest of time, what I'm going to show here is just a kind of a quick experimental way of gauging the polarization. That's by looking at the passage versus the feed flow. So what we're essentially doing here is scanning through crossflow velocities. So 3 GPM is high crossflow velocity. The concentration near the surface is essentially pretty close to the bulk. And as we start starving the crossflow, two things happen. One is the recovery goes up, and the second thing is the mixing starts suffering. And what this line is really showing is that for the 28 mil mesh and the 19.5 mil with our current print pattern, the polarization is essentially the same for both of those. Those curves overlap. The effect of polarization as a function of feed flow is the same. So that's a good thing in terms of performance. It's also a good thing in terms of how we project system performance, because that allows us to leverage a lot of the work that's been done before with film theory as a way to be able to predict polarization at different flux rates, different cross-flow rates. So with that, we'll jump from some of the theory into one specific case study, and then we'll get back into the theory a little bit about why it's working the way that it is. But this is showing some performance from a system that we've been running for a bit over a year now at Micron Semiconductors. This is the system that was being mentioned before. It's a reject recovery system. So it's taking brine from different parts of the plant and recovering water back to the front to reduce the water footprint. And what the goal was here was to reduce the energy consumption. Now, the specific plot here, we've got x-axis is time, obviously. The top two lines are the feed pressures on the left axis. Orange is for the mesh elements. Blue is for the printed elements. And then we've got kind of a blow up of the yellow and the green of the pressure drop, which are on the second y-axis on the right. You can see that the immediate drop in the pressure from the mesh to the print, and we'll get into a little bit about the different factors that cause that reduction. But before we get into that, I think it is worth pointing out some of the specifics of this are relatively unique in terms of looking at field performance. And that's because there's two systems that are running in parallel at the same time on the same feed. We rolled one set of elements with a mesh, one set with a print. So it's about as close a comparison you can have with just the feed channel changing, especially over this time frame. So both systems are running the same flow rate. They're both producing the same gallons per minute at the same recovery, and the pressure is allowed to adjust to hit that. So we see the immediate reduction and the ongoing reduction in terms of the energy savings. The pressure drop is blown up to give a sense of how things are changing over time. So the green is the printed pressure drop. You can see it's relatively constant throughout. The yellow is the mesh. And what this is kind of highlighting is the effect of channel plugging over time. As that system ran, the feed channel became less and less efficient at passing water through, took some more pressure to get through as solids began to accumulate in that channel. So at that point, I will jump over and start going into a little bit more of the sort of the theory of how this works. Before I do that, I wanted to flip over to our projection software, because that's what we're leveraging to get in the sort of the why these energy savings, pressure drop reductions are being observed.
Yeah, just one comment quick before CJ jumps to the next slide. And the Micron there. On the Micron slide, you see here one of the questions we get often, and CJ just talked about it on concentration polarization, is quality. So obviously, Micron and most customers aren't going to give up quality. So just one other added point there, CJ talked about, hey, same flow rate, but it is also the same quality. And that's one of our limiting factors as we optimize pressure drop versus mixing. We always have to make sure we maintain the same salt rejection, because ultimately that's what the customers are buying. So just wanted to add that point, because we get that question a lot. This data was presented with Micron at Semicon West last year, part of our case study. You can learn more about it in the full write-up.
Right. So let me flip over to our projection software. This is done in conjunction with a company, Clear, who developed a.
Yes. You share your screen.
Oh, I have to reshare it. Okay.
Yep.
Let's try this one more time. And I'll probably have to do this one more time when I flip back to slides. Okay, are we now seeing?
Yes.
Okay, great. So this is our projection software. A lot of this should look pretty familiar. Maybe the biggest difference is that it's in a web browser, which ends up working well. We have a certain amount of functionality in being able to send an invite to people to open up a projection. If you've got a question, you can send it to us. It's pretty easy to share, work collaboratively on this. A few different tabs to go through. One is the water type. This is just a sample water type that we set up based on a groundwater. There's a typical tab where you input the system design, so the type of element, the array that's being used, how things are set up. For the specific example that we're looking at, it's a 3-stage, 15 vessel, 10 vessel, 5 vessel, all 6 long. But what I really wanted to get to is some of the comparison. So with this specific system, the idea was to target the same 100 GPM. We can compare some different systems. So if we use the eco, you can quickly see a pretty significant reduction in feed pressure. The main reason to kind of recognize that the difference, it kind of comes back down to 2 things. One is the flux. Because we've got more active area, we're able to reduce the driving pressure, because we don't need to run as much through a given square foot of membrane because we have more square feet. And then the second thing has to do with these slopes of lines, the pressure drop. We've got less pressure drop as it goes through, which results in a more balanced flux profile. So in addition to being kind of a lower average, you can see that these tail elements with the printed channel have a higher flux rate. So it's kind of a nice tool to be able to look at different types of membranes and get an understanding of what's going on differently between each of those. So let me flip back to the PowerPoint here and get this going one last time. Okay. And so then the last couple of slides are going to be highlighting what was going on in the specific system, where the energy saving was coming from. So before we ever loaded the system, we had done kind of similar projections of the system at the Boise Fab. First slide is looking at feed pressure. You can see the energy savings. It's relatively simple math to convert these feed pressures into what we're maybe most used to thinking of in the water space, the kilowatt hours per cubic meter, the specific power. And you can end up getting a pretty close to the observed 19%, I think it's about 20% energy savings from that difference in the feed pressure. But that doesn't really explain where the energy savings was coming from. And that's where this next plot gets to be a little bit more useful. We can look at the difference in the pressures that was driving water through the membrane. That's the transport. Some of the pressure ends up being released in the form of the brine. That's the pressurized brine. You'll note that's about the same because both of those has the same flow and pressure coming out the back end. Pressure drop, as we talked about, kind of pressure drop through the system, much lower for the print. And then all of these systems, both of them were feeding a relatively high feed tank. So there's a back pressure in the permeate. And so we can pretty accurately break down where the power was going. And as you can see, the savings was essentially split between the transport and pressure drop, which makes sense kind of based on the increased active area and the more efficient flow through the feed channel. That was all in modeling form. We can, also look at how the actual system startup performed to get a sense of sort of the accuracy of the projections. Both the mesh and the printed were modeled on the same platform. We do have the ability to look at a lot of different types of membrane element constructions and membrane flat sheets with these comparisons. So the red are the meshes, blues are the prints, and the bolds are the experimentally measured values. As you can see, pretty good matchup on the feed pressures, which then correlates into the hydraulic specific power. But we also did measure amp draw to get the specific electrical power, just a little bit more because of efficiencies in the system. And with that, I will pass it over to Ben Schultz, our marketing director, to finish things off here and lead into the questions and answers.
Hi, my name is Ben Schultz. And today, we're gonna go over some of the Q&A. First, I want to get started with some questions that we got. In the Q&A section, you can ask any questions that you might have through the presentation now, and we can answer them, or any questions that we haven't covered that you were hoping to answer. We'll try to answer those quickly. First, we had a question for CJ. He said, in the mesh versus printed spacers diagram, we see some measurements with 400 square feet and 440 square feet with mesh, the blue dots, and the less than 440 square feet with printed spacer, red dots. Do you have any actual measurements with printed spacers and active area, and an active area 400 square feet or 440 square feet?
Yeah.
So that's quite a question, but
yeah. And let me pull that slide up again just for people to recall. So that's the slide here. The question is, the data as we start to go farther and farther down here. We do have data with thicker channels than we're showing here a 20 mil print height. This is about a 22, 23 mil. We have made thicker channels, but the measurement of pressure drop gets to be difficult because it is such a low pressure drop. Most of the time where there's interest in print heights kind of above a 22 mil get to be different types of feed streams where viscosities or solid levels start to influence pressure drop more than just the flat sheet membrane. So if we were running on a sugar solution or something that with a high viscosity, those would be the times where we would look at being able to push that down. Kind of similar to the way that some spirals in process industries start to push 46, even thicker channels than that. but the applicability in the water space is limited. So for this one, we're not showing lower. We would really go to different types of challenges to be able to start quantifying those even thicker channels, things that start to be the same thickness as the current.
Great. Great, thanks, CJ. Another question that we've gotten on the side is, we talk about channel plugging and the effect of printed spacers on scaling and fouling, but we didn't go quite into it. In the micron data, we see the delta P, we see that there's a big drop off. Are those cleaning intervals, or is that something else?
And once again, I will pull up the data here so that it's a little bit easier to see what we're talking about. So the kind of question is about these drops here, what's going on with each of those reductions. There's a lot of things going on in these systems, and to a certain degree, I think it's useful to recognize that it's almost amazing the data is as clean as it is, because this is a system not being run for data. This is producing water inside of the plant. Those specific points where things were dropped didn't correlate with cleanings. What they did seem to correlate with was periods where the system had shut down and then started up quickly. So if anything, it seems to be more of a difference in terms of potential, almost early stages of element telescoping. So sometimes when things are hit with a hydraulic kind of water hammer, there's a force that, especially with a mesh netting, can end up displacing, especially certain portions of the feed spacer net. And after that shift has happened, there's a reduction in the pressure drop because there's channel spots, there's spots that are more open. That also corresponds with locations, though, where mixing is no longer balanced. There's thicker channels where most of the flow is going through, leading less flow for other areas. And what we ended up seeing was actually faster rates of pressure drop increase sort of after each of those pressure reductions that occurred. One of the points that may be worth talking about too is if you look at the location of the pressure drop, and I'm not showing this here, but we can also look at the pressure drop across the first stage and compare that with pressure drop across the second stage. These are two-stage systems. And what we ended up finding is that most of the increase in pressure drop was from the first stage. That gives us a little bit of insight as to what was occurring, what was the cause of the pressure drop increase. Because most of the time, if a system is scaling, the pressure drop increase occurs in the second stage where the concentrations are higher. Since this was occurring in the first stage, that's more consistent with a biofouling event. So not conclusive point there on kind of the origin of the mechanism, but some indication that this specific site was seeing some differences in terms of biological fouling.
Great, thanks, CJ. And then another question is for Craig. Do these membrane elements work with a certain type of chemical, a cleaning chemical, or are they limited to any cleaning chemicals?
Yeah, good question. We get that a lot. I mentioned in the intro, our elements are directly interchangeable. So they're standard size 80/40s and directly retrofittable into systems, and also directly compatible with standard RO cleaning. So if you're doing low pH or high pH or surfactant cleanings, any standard off-the-shelf reverse osmosis cleaner is compatible with both our membrane elements and specifically the resin that we're using, the polymer we're using for the features we're printing on. The one exception to that is very high temperatures. So for example, in the dialysis, some food and beverage, and certainly in the dairy industry, temperatures are taken up to 85, 90, sometimes even C. Our technology is not yet compatible with that application. We have some developments of some new product that we expect to introduce late next year that will get us to that. But for all water, wastewater applications, kind of standard operating temperatures, all the way up to 50, 60 C, even in a cleaning regime, no problem. And all the pHs, yeah, compatible.
Great, thanks. And then this is another question for CJ. That's about what about turbulence needed to reduce scale formation? I could imagine that in printed spacers, the turbulence is reduced.
So with scale formation, there's sort of two pieces. So one is the polarization piece to try and keep concentrations of the surface to a point where scale formation isn't any worse. The second piece is actually less about turbulence and more about shear rates in different locations. So what we've ended up finding with a lot of the installations that we've been running is that, you know, the concern isn't like an average degree of turbulence, an average degree of mixing. It has to do with locations where shear is much lower. And so in the mesh, although there's, you know, a fair bit of turbulent, not quite completely turbulent, there's some regions where there's turbulent flow. But there's also some regions right behind feed spacers where there's almost like a shadow area. There's very low mixing, and those kind of regions are connected by the strand that kind of makes it through the element. And so with scaling and to some degree biofouling as well, what we've found is that the performance of the printed spacer is made more beneficial by the fact that the isolated kind of points that we print on the membrane surface are each isolated. There's not the ability to start depositing and then crystals to form, and for those to, you know, almost like have a percolation network that allow that to start kind of, you know, taking over the overall element. So sort of two pieces there. One is about the shear rates, shear velocities. Then the other piece is about the average polarizations. We've hit both of those.
All right, and then we have two questions, similar a bit in nature. One is, what types of maintenance are required for aqua membranes in the case of wastewater treatment, periodic backwashing or chemical cleaning? And then also, what is the life cycle of a printed membrane versus a mesh membrane? For you.
Yeah, I'll start maybe with the second question, and then I'll answer the first one, and then CJ will make sure I answer it correctly, which is what he always does, checks my answers, because I know just enough to be dangerous. On the cleaning and life of the element, it's really tough to say the life of the element until the end of the life of the element is done. And we have not had installations running long enough to get to a standard membrane element life, thinking maybe 3, 4, 5 years, depending on your application, cleaning, et cetera. But as CJ presented the Micron data, that's really our best indication that's public data. We have some other data that's still confidential, we can't share, but the best predictor of life typically has been pressure drop increase. So as your pressure drop increases over time, cleanings, backwashes are done, and then hopefully that brings that pressure drop down, and then it grows and goes up and down. And you get kind of this sawtooth increase over time graph that eventually you get to a high enough pressure drop that that's starting to damage your elements, or that pressure drop is an indicator of another problem, which is, as CJ said, channel particulate buildup that both slows down your flow and affects your quality. So membrane elements are typically replaced because you can't make quality or quantity, or the pressure drop is getting so high you could actually physically crush the element. So that's the predictor of life at that Micron site. If you draw that out into the future, let's say that they had 50, 60 PSI of total pressure drop on their system, and they're like, yep, that's the end of the life. We've got to replace them. If you graph that out based on the preliminary data we have, maybe that's 3 years, which is indicative of kind of past life they've got in that application, because it is a challenging application, concentrating stuff that was already concentrated. Now, if you take our same graph for the printed spacer technology and graph that out, when does it hit 50 or 60 PSI? It's a long, long time into the future based on the slope we have now. Now, it's a year. It's not 3 years. It's not 5 years yet. But preliminary indication would be that technology with our printed spacers, membrane elements, will last significantly longer. Is it 50% longer, 100% longer? We don't know yet, but we do have data at a number of sites that is early indicating the membrane life will be significantly better with our technology. From a cleaning standpoint, again, standard procedures with other reverse osmosis elements are same for ours, with the one benefit, maybe addition of we could backflow. And when I say backflow, I don't mean permeate side to feed side, but concentrate to feed side. It's not typical in a membrane application to reverse the flow through the housing. So if you go right, left, right through the housing banking arrangement, you do that same thing in cleaning. We could actually flip and reverse that very easily because our features are attached to the membrane surface. Whereas with a mesh, you get some of that movement CJ was talking about before of like extruding as you have high pressure drop, but even just reversing the flow, it moves just a little bit, and that could actually cause a scratch or an issue with the membrane surface. So in reality, our membrane elements have a bit more variety in the methods that they could be cleaned than the standard elements with mesh. CJ, anything I went off the reservation there or off Pueblo?
No, nicely answered.
All right, I think. All right, I think that wraps it up for the questions. As we come to a close here, I just want to go over a few follow-up things for anybody that might be interested in getting in touch about more details of using Aqua Membranes elements in their application. So we have two products that we can provide you for either the applications in large commercial quantities right now. We have the Eco and the Flow element. The Eco is what we brought up that's been used at the Micron site for the energy savings and that we've seen with the longer membrane life so far. And we also, if you have a system where you're struggling to meet output goals, we can use that added area to maximize your productivity and your output without having to add any additional equipment. So these are the two, we have this brochure available on our website, or if you contact sales@aquamembranes.com, we can surely send it over to you. Also, for anybody who is interested on this meeting, if you have a project that you're thinking of now, if you get that started with us, we do have a discount that is going to be provided for this webinar. So please reach out to sales@aquamembranes.com. If you attended the webinar today and you want any extra details that we didn't provide, or you have a specific product that you'd like, project or system that you would like us to run a projection on with you, we have resources available to get you some great predictions on how our membranes can improve your operations. Feel free to reach out at sales@aquamembranes.com. But thank you so much for everybody for attending today. And I think we will wrap it up there.
Thanks, everybody. Take care.
Thank you.